Think of Ethereum as the trust anchor. Layer 2 systems can process activity off-chain for speed, then submit results back to Ethereum for finality, security, and verification. That settlement role is the foundation for understanding rollups and privacy systems. So far, we've seen why scaling is necessary. Demand keeps growing, block space is scarce, and fees rise when users compete for limited capacity. But Ethereum cannot simply increase throughput without weakening key trade-offs, like decentralization and security. The next idea is architectural. Ethereum can remain the trusted base layer, while Layer 2 systems handle more execution off-chain. That sets up our path into the Layer 2 landscape and rollup user experience. A settlement layer is where outcomes become final. It is the official record everyone agrees to trust. Ethereum can serve that role by securing balances, contract states, proofs, and commitments. Other systems may process activity elsewhere, but they rely on Ethereum to confirm the final valid state. Execution is the work of running transactions, checking inputs, applying smart contract logic, and computing the new state. Settlement is the final record, deciding which result counts, handling proofs or disputes, and anchoring finality to Ethereum. On Layer 1, these functions are bundled together. In many Layer 2 designs, they are separated. The Layer 2 performs fast execution, while Ethereum provides trusted settlement and security. On Ethereum Layer 1, a transaction goes directly into the base network. Validators choose and order transactions, then include them in blocks. The Ethereum virtual machine runs the smart contract logic and updates balances, storage, and contract state. Once that block becomes part of Ethereum's canonical chain, the result is settled. Layer 1 is doing both jobs, computation and final agreement in one system. Ethereum is a programmable state machine, not just a ledger. Its state includes ETH balances, contract storage, token balances, and application data. A transaction is the trigger. When it calls a smart contract, the contract's rules determine whether the transaction is valid and exactly how state changes. That might mean moving tokens, updating a lending position, or recording a vote. Rollups follow the same idea, but compute much of that state off-chain. A state transition is the move from one valid system state to the next. Transactions are collected, and only those that satisfy the system's rules can be applied. Executing them changes, balances, contract storage, or ownership records. A rollup performs this work off-chain for many transactions at once. It computes the new state, compresses the result, and submits a commitment or proof to Ethereum for final verification. A blockchain state can contain millions of balances, contract variables, and positions. Instead of sending all of that to Ethereum, a rollup can publish a compact commitment called the state root. Think of it as a cryptographic fingerprint of the entire state. If even one balance or storage value changes, the root changes too. This lets Ethereum compare states and verify proofs while most data stays off-chain. Finality is like moving from a draft agreement to a signed, enforceable contract. A Layer 2 can process activity quickly, but users need confidence that the result cannot be casually rewritten. Settlement on Ethereum provides that anchor. Once outcomes are posted and accepted by the base layer, bridges, withdrawals, and balances have stronger guarantees. It also limits the power of any single operator, because enforcement comes from Ethereum's public security rather than private promises. Layer 2s borrow Ethereum security, but that security does not appear automatically. They assume Ethereum validators continue agreeing on the canonical chain, and that incentives make attacks expensive and punishable. They also rely on public verification, so anyone can inspect transactions, contracts, and posted data. Most importantly, Ethereum must remain live enough for users to submit proofs, exits, or challenges. These are strong assumptions, but still assumptions. If Ethereum weakens, Layer 2 security weakens with it. Execution can happen off-chain, but verification depends on what data becomes public. A rollup may post full transaction data, compressed data, or state commitments to Ethereum. This gives users and independent verifiers a shared source of truth for checking balances and proving exits. If the needed data is unavailable, trust assumptions increase because users cannot reconstruct state themselves. Data publication is both a security requirement and one of the biggest scaling costs. Layer 2 systems need a way to convince Ethereum that their results are correct. One approach is proactive. Submit a validity proof, and Ethereum verifies it before accepting the update. Another is reactive. Publish the result, allow a challenge period, and let disputes expose fraud. In both cases, Ethereum's smart contracts enforce the final outcome. That is what makes a Layer 2 operator much less trusted than a normal centralized service. Layer 2s get speed by executing many transactions away from Ethereum, but they inherit security only when important facts are anchored back to Ethereum. Deposits, withdrawals, state commitments, and proof or challenge rules. The settlement contract acts like the referee. If the Layer 2 design is correct, users can fall back to Ethereum enforcement when something goes wrong. Imagine a DeFi app launching on a Layer 2. Users get cheap, fast trades immediately, but the strongest Ethereum security arrives when transactions are posted and settled. That gap affects product choices, how fees are shown, how withdrawals are timed, and what risks are disclosed. Protocol teams must inspect data availability, bridge logic, and operator powers. The key question is simple. What is secured by Ethereum, and what relies on extra assumptions? The big idea is separation. Layer 2s execute transactions at scale, then use Ethereum to settle, verify, publish data, or enforce outcomes. State smart contracts and state transitions make that possible. Next, we'll map the Layer 2 landscape, then connect it to everyday rollup user experience.